Perfect. Thank you, AI. All right. So tonight's agenda. First of all, introductions. Are anyone here in the room that is new to HAL, that has come, your first time here? Wonderful. Wow, wonderful. That's fantastic. Would you like to introduce yourself?
Hi, I'm Allison. I joined last summer because I wanted to see the meteor shower, and the weather's been awful every time. I live in the city, and every time I'm willing to schlep out here, the clouds are.
Welcome to the world of amateur astronomy.
It doesn't seem worth making the trip.
Yeah.
But I figured these pictures were going to be too good to see on my computer. So
absolutely,
I made
yes.
the trip, and I got here a little early and walked through the woods. So.
Yep. No, you get them on the big screen. Absolutely, that's way to do it. So, who else? I saw other hands, new people. Yes, sir.
My name is Sundar. I joined this club 6 months back. This is my first meeting, and like she said, watching seeing those pictures here in person, would be amazing. And also, I'm here to get the lunar Earth.
Yes, sir.
Yeah.
Now, for what he's referring to, and we'll have a slide on it, is the HAL Seestar loan program. So Sundar is going to be picking it up for the next month, and he'll be able to make use of it and hopefully get his own beautiful photographs out of it, which will be exciting. So we will expect pictures from you next month in the Astronomy. Okay. All right.
My name is Mike.
Hey, Jim.
Hang on one second, Wayne.
I'm here. My name is Mike O'Cronic, and I'm here to sign up.
Oh,
for the
okay.
meeting, and I'm here to basically learn more about astronomy.
Well, welcome very much. We're happy to have you. And Ken, maybe you can help in terms of directing him how to sign up.
Sure.
So Wayne, you had something? Uh-oh. Wayne, did you want to say something, or?
Yeah, I just wanted to let you know, I'm not sure you can do anything, but ours online, the sound keeps cutting in and out.
Yeah, I'm not sure because I don't think that the connection here is super robust.
Kind of tinny.
And I think I've got everything else shut down on my machine.
Do you have the volume up?
Yeah, I have the volume. Okay, so let me see if the.
Okay, we're only catching about half of the words.
Are you hearing the good word?
I am. I guess I won't.
No, that's happening to me also. I'm glad you brought it up.
All right, I just changed the microphone to the laptop.
Is the microphone far away from the speaker?
Okay, I just changed from the microphone from the camera here to the laptop. Is that any better?
Now you sound far away. You sound farther away.
Yeah, you're soft, but it's at least getting.
Okay. So I guess we'll just have to project here when we have this. Okay, anyone else here that's new? But yes, sir. Well, welcome, Frank. Glad you could join us this evening. And the gentleman back there, you're new? I won't, yeah. Absolutely, yes. Great attraction. Yes, sir. Well, I hear that a lot. I mean, I know personally for me, there was a period where I probably went about 20 years, what with family and everything, but it's a hobby that you can get back into pretty readily. So welcome. I'm glad you're here this evening. Oh, okay. Now, hopefully you can, make some connections and that'll work out. Is there anybody online that is new that would like to say hi?
Hi, this is Brittany Glauser. I just joined today and looking forward to meeting all of you guys and seeing some great stuff in the sky.
Awesome. That's great. Thank you, Brittany. Wow, this is amazing. I mean, I don't think we've had this many new people at a meeting. Kelly, we're going to have you back next. I mean, you're just a magnet here. All these people are coming out of the woodwork to see your presentation tonight. That's awesome. Anyone else after Brittany online? Nope. Okay. Welcome, everybody. Okay, so the Seestar program, wanted to kind of basically touch on that. For those of you that don't know, we have a program where the club last spring bought a Seestar, which is a AI highly automated telescope, not very large, 50 millimeter, but if you go online, you can see some amazing pictures. The hardest thing that I understand about the Seestar, I've not used it before, Ken has, is getting it level. But it's like, once you get it level and you tell it, you know, what you want it to go observe, like I want you to go photograph the Orion Nebula, or I want you to go photograph the Lagoon Nebula. It will actually find it, center it, and start taking exposures. And then you can download it to your phone, right, Ken, or pad, whatever.
There is no eyepiece, so it's basically completely controlled by the phone.
That's a good point. This is a imaging only telescope. There is no eyepiece with it. But this is a cool benefit. If you're a HAL member, you can go online. I've listed here, and Ken will be putting the slide deck out on the website. And basically, you can go to the website, click on the link, and register. So the next few people, as we said, Sundar is here this evening to pick it up for the next month. Then after him would be Salman, and then Christopher Roper. So that's, you know, the next couple people, and it's not a long list. So if you're interested in taking the Seestar home for a month, you know, check it out. It is for members only. Yes, you have to be an active member.
Hey, Jim, just so you know, you're still cutting out.
Okay, Wayne, I don't know that there's anything I can do about it. I just think it's the internet connection here. I'm sorry.
Yeah, I know. I don't know that there's anything you can do, but if we're quiet on this end, that's why.
Okay. In terms of star parties, our next member star party is August the 3rd. Our next public star party is August the 10th. So there should be a good opportunity, if we get clear skies, of seeing a few meteors, because that's approaching the Perseid peak. There was a star party. We were just talking about it before the meeting kicked off last Saturday. Apparently it drew about 100 people. And even though the skies were fairly overcast and not ideal, which is a great testament to just how people are interested in what's going on up there. Also, HAL participated. A few members went to the Smithsonian Summer Solstice Astronomy Festival. That was on the Mall in Washington, D.C. Victor gave us a report at the board meeting. He said there were literally thousands of people out on the Mall. There was lots of networking. He handed out a lot of HAL cards and brochures. Really good outreach opportunity, according to Victor. He said that he had a line, you can see there on the bottom right-hand side, he had a line of people at his scope until 11:30 or 11, and he actually had to stop it by having his daughters go to the end of line, kind of like how when you're at a checkout line and the cashier wants to leave and she goes, you know, you don't let anyone else behind you. So his daughters went out there and did that. Otherwise, he probably would still be there showing people M13. So, I mean, it was just a very, very successful event. And I know Victor is excited next year. He wants to do something a little bit more participation from HAL if possible, but it was a great event. Yes, Sundar.
I was there.
Were you?
I was standing in the lane. I could not stand in the lane for a long time. So I left the lane, I said, hi, sir, and then to the rest. I could not wait for my turn.
It's like Disney World. Come on. Yeah, that's really, again, it's kind of a testimony to kind of what draws us to that great universe out there. So But that's interesting. And he said it was really hot too. I think that probably made, yeah, that makes it hard to stand in the lines as well, I think. Well, that's nice. Yeah. Well, that's great that you took the time to say hi to him. All right. The other thing that Victor wanted to be sure to mention was a big thank you to Thorne Ransom, Ken Evanhart, and Gary Richardson. Along with Victor, they gave up their time on a Saturday to kind of clean up and rehabilitate the halo. You can see the before and after pictures there of the dome. They did a remarkable job of getting it all nice and clean. And it really looks cared for and it looks beautiful. And so our thanks to these guys, these HAL members who of their own time, you know, pitched in and came out to make sure that Halo is in good shape. Okay, the book of the month for this month, it is Night Sky Atlas. Crystal, I think I saw you online. Would you like to unmute if possible and talk a little bit about this book?
My name's Crystal. I'm the HAL's librarian. So yes, today's book of the month is Night Sky Atlas. So the version that we have here, which I'm going to try to hold up here in a second, the version we have is edition published by DK Publishing, which includes a CD-ROM. Unfortunately, none of my devices have a port. It's pretty amazing. So our edition does in fact still have the CD if you're interested in giving a shot. I just don't have a device that can play CD. So you might recognize that I had this book out during the most recent public red light activities tent that I had set up. So this is it. And I actually came across it by accident. So I was looking at the shelves for something to show constellation patterns. And I really got to tell you, this is like one of my favorite like we look at. It gives you great information about terms, how to use the atlas. But the thing I love the most about it is layout. So the first thing is that there's these constellation pages. And the great thing about constellation pages, yes, you get to learn more about constellations, but they also have this really cool feature, which I'll try to flip to and just where you can learn not only like, you know, what is the constellation, but it has these really awesome, I don't know how well it's going to show up on camera, but it has these like clear plastic overlay sheets. So if you flip, you can see behind it a nice clear photograph of the night sky. And then you flip it back, what's actually there is little dots of reference. So it traces out the constellation name, deep sky objects. But if you're more interested in not seeing the overlay, you can flip it away and just see the night sky. So this little feature was fantastic because if you're just learning how to navigate the sky, it can be a little like, oh man, there's all these lines and names and things. And if you're not as familiar with it, this is a great way to have like both the solar system. And it is by DK Publishing, so you know that the diagram visual is really well done. So I highly recommend this. The one downside is while we have a copy in our HAL library, this 2007 edition is very hard to order. You know, if you're looking for it online, you might not be able to find it if you're looking for the one that comes with the CD. If you're interested in checking it out, just come and see me. I also have a public star party at Glenelg Country School tomorrow where I plan to use the book as well. So if you'd like to check it out afterwards, you can either email the librarian or drop by and see me at the next public star party in August. So there we go. That is your book of the month.
Thank you, Crystal. That's a great choice because I know there are times when there are people who are just getting into the hobby And that is one of their main questions, is how do you make sense of, you know, these fantastical creatures that are supposedly in the sky? And so that would be a great resource. And as Crystal mentions, that is in our HAL library out where Halo is. So if you're interested, you can, if you can't find it online, you could always check it out of the HAL library. Thank you. Okay, so for this evening, our main feature is Dr. Kelly Lepo, who is Lepo, and she is has been education and outreach scientist at the Space Telescope Science Institute here in Baltimore on the Hopkins campus, supporting outreach efforts for the James Webb Space Telescope. Graduate from University of Toronto with a PhD in astronomy and astrophysics. During her time in Canada, she made numerous local and national media appearances to talk about everything from the 2012 Mayan apocalypse. Remember that. Remember, everything was going to end because the Mayans had run out of their calendar. And the super blue blood moon. In other words, I think Kelly kind of defends us against bad science and bad press. You know, the thing people go, where's that red, blue moon, wolf moon? No. She has also served previously as coordinator of the McGill Space Institute, taught physics at Gonzaga University, and was involved in the building of the Large Hadron Collider at CERN. And we did not disappear into a black hole, despite her best efforts. So Kelly, I'm going to stop sharing. If you would take it away, I guess maybe up here you can probably be heard better. I don't know. Let me stop sharing. So welcome.
Yeah, I think so. Let's try. Any better? Okay. And then.
And we're getting a feedback.
Okay. Okay, no feedback? We're good? Yay, okay. Now to share my screen. Share Microsoft PowerPoint. Oh, and
We just need to change.
Yeah. Unplug you. In. Sorry.
Got you on screen.
There we go. And I'm share
Perfect.
PowerPoint.
We lost it online. There it is. Thanks.
Okay. I think that should be good. Everything good online?
Yeah, checking.
Okay. I think pull up the chat here. Oh, okay. No, no one's yelling at me, so I'll assume I'm okay. So hi everyone. Thank you so much for having me today. My name again is Dr. Kelly Lepo. I'm an education and outreach scientist at the Space Telescope Science Institute. And tonight I'm here to talk to you a little bit about 2 years of the James Webb Space Telescope. So it is from this rather unassuming looking office building on the campus of Johns Hopkins University that a lot of really neat things happen. So we at the Space Telescope Science Institute, STScI, support 3 different telescopes. We are the science operations home of the Hubble Space Telescope. We're also the science operations home of the upcoming Nancy Grace Roman Space Telescope. And we are the science and mission operations home of the James Webb Space Telescope. So what does that mean? So science operations involves helping astronomers to write proposals to say what they want to observe with the telescopes. It also, we coordinate the process by which a panel of peer reviewers select the best proposals for the telescopes to see what they're going to observe. We also do pipeline stuff to allow astronomers to download and process the data. And we also store all of the data in the massed archive. So that's science operations. Mission operations is the fun thing. That means a couple floors above my office is the Mission Operations Center, and they don't let me do this. I just get to go and give presentations like this. But the people there, a couple floors above my office, they send commands up to the telescope. They set the schedule for the week for what the telescope is going to observe. And they downlink data from the telescope about twice a day and monitor the health of the telescope to make sure that everything is going well. So speaking of the telescope, the James Webb Space Telescope launched from the European spaceport near Kourou, French Guiana on Christmas morning, 2021. I don't know what you all were doing, but I was dressed up in my fanciest pajamas. I had my little mimosa and I watched this. We all got really excited. And here is our last view of JWST as it is sailing off to its parking spot about 1 million miles away from us. So everyone say goodbye, Webb, good luck, and send back lots of really cool pictures. So where is JWST now? As I said, it's about 1 million miles away. It's at this special point called L2, the second Lagrange point. It's this point that follows the Earth around as it orbits. It's a gravitational balance point where the motion of something small, like a telescope, can balance the motion, or the motion of the telescope can balance the gravity from the sun and the Earth and the moon. We have to put the telescope so far away from us, partially because it is a cold, stable environment, and also because we want to get it away from that heat, again, of the sun and the Earth and the moon. What else was I going to say? There's also other telescopes out at L2, including Gaia, and what else? A couple other telescopes, but never fear, space is very big and these telescopes are in these big halo orbits. It's actually larger than the orbit of the moon around the Earth, this orbit that JWST is doing around L2. Partially that's because JWST is a solar powered telescope. So if it was exactly at L2, the Earth would always be blocking the sun, and we can't have that. So it's doing this halo orbit. It requires a little bit of propellant to maintain this orbit, just a teeny little bit. We have more than 20 years of propellant on board. So something else will probably go wrong with the telescope before it runs out of propellant. What that is, I don't know. If I knew, they would pay me a lot more than they do. So we'll see. Maybe the computer will fail. Maybe the mirror will get hit by too many micrometeoroids. Maybe some detectors will stop working. Who knows? JWST is mostly an infrared telescope. Hubble, which most people are familiar with, is mostly a visible light telescope, the type of light our eyes can see. It sees a little bit into the ultraviolet, a little bit into the infrared. JWST really specializes in light that's from the sort of reddy orange part of the visible spectrum, about the color of its mirrors, all the way into the mid-infrared. So why do we look at space with different wavelengths? Well, every time you look with a different type of light, you learn different information. So here we have some meerkats and a freshwater crocodile. Looking at them in visible light, you can see the meerkats are very cute. They have cute little fuzzy tummies, and you can see the scaly texture of the freshwater crocodile. When we see them with an infrared camera, what we see is the cute little bellies of the meerkats, in fact, are glowing. That's because they are warm-blooded. They are warmer than their surroundings. And everything that's about room temperature, so you and me and the computer I'm talking into, and everything else in this room is glowing very brightly in infrared light. So these meerkats are glowing very brightly in infrared light because they're warmer than their surroundings. But the freshwater crocodile, on the other hand, it's about the same temperature as the ground. And so it's about the same brightness as the ground looking in infrared light. And I'm not lying when I say I'm glowing in infrared light. So here's a selfie that I took with an infrared camera. And you can see that my skin is a little bit warmer than my clothing. And that is because I am glowing in infrared light. So here's something else that's glowing in infrared light. Here's a star. This is the first telescope. This is the first image, or one of the first images that JWST sent back after all of its 18 hexagonal mirrors were aligned so that they were functioning as one mirror. So this happened in the first 6 months after the telescope launched. It was parked at L2. We aligned the mirrors. We turned all the instruments on. And this is one of the first images we got back. And we are all really excited. So ignore the star for a minute. You can look in the background and there's all those little dots. And if you look really closely, you can actually see some of these dots have little spiral arms. So almost every single point of light in this image is a galaxy. So Webb, just in taking an image to see if its mirrors were aligned, has taken an accidental deep field image, which is wild. But anyways, let's go back to the star in the middle of the image. You'll notice there are spikes coming off of the star. And as amateur astronomers, you're probably familiar with this concept that anytime you have a telescope with mirrors, you generally have what are called diffraction spikes. And Webb has this very distinctive diffraction spike pattern. And that's caused by two things: the shape of its mirror and also its struts. So here we have Hubble versus Webb, and Hubble has a sort of more normal Cassegrain telescope design with a circular mirror and 4 struts, and it makes this cross-shaped diffraction pattern. So you'll have, with bright stars, you'll have a little bit of fuzz around the stars and then four points pointing out of it. For Webb, you will have this distinctive shape where you have 6 big spikes and 2 little spikes. And that is caused by a combination, as I said, of the mirror. So basically, anytime you have a flat edge on your telescope mirror, you get a spike. So hexagon shaped, 6 sides, 6 spikes. And then also it has 3 struts. And those 3 struts also make a 6-pointed star shape. That one's more squished. I like to call it an X-wing shape. And this was designed by the very clever engineers who built the telescope to overlap a little bit. And that's why you get the shape that you do. So it's very easy if you're looking at a space telescope image to tell a Hubble image from a Webb image, count the spikes on the stars. Some people ask me, if it's an infrared telescope, how are you making color images of it? And the same way we make images from Hubble, we use something called chromatic order. So we take images of objects in space with different filters, and we take the shortest wavelength and we assign that blue. We take the longest wavelength and we assign that red. And we pick some filters in the middle and assign them green, or I guess here orange or teal. And then we combine them together to make a color image. It's a little bit like taking a scale and transposing it into a different octave. And then we take this raw image and our image processors fiddle around with it a little bit. They adjust the white balance and the color and the contrast. It's a mix of art and science, and then we get a final image like this. This is the JWST image of the pillars of creation, and we'll come back to this in a minute. One other little piece of housekeeping here is that I will be showing you a lot of pretty pictures tonight, but just keep in mind that JWST is primarily a spectroscopic instrument. So by spectra, I mean taking the light and splitting it into its component colors. And using spectra, you can tell things like what something is made out of, how dense it is, how hot it is, how it's moving. You get lots more information from that. So something like 70% of all of the observations that Webb takes are all spectra and not images. And Webb has several different types of spectrographs on board. My favorite one here is called an IFU, an integral field unit. And what this can do is it can actually chop up an image and take a spectrum of every pixel of an image. And this is useful for everything from understanding how a galaxy is rotating to finding the composition of an icy thing in the outer solar system. So I'll be showing you some IFU images later tonight. Okay, so we have launched our telescope, we have sent it out to L2, we have aligned all of the mirrors, it works, and now here we are celebrating the anniversary this month, the second anniversary of JWST science. Yay! So this is the first science image that we released. I got to see it a couple days early. I was really excited. Perks of the job. But this is SMAX 0723, Webb's first deep field. And so in this image, I really do like it because you get basically the entire universe in one image. So the bright things with spikes are stars. They are stars within our own Milky Way galaxy. And then looking beyond that, you see the sort of white oblong things in the middle. Those white fuzzy things are galaxies in a galaxy cluster, SMAX 0723. And then if you look around that, you'll see these arc-shaped things. And that is because this galaxy cluster is so massive that it is warping the fabric of space-time. And it is acting like a lens, a very lousy lens, but a lens nonetheless, like looking through the bottom of a wine glass. And so the background galaxies that shine through the galaxy cluster make these arc shapes. And these arcs, galaxies are bent, but they're also magnified. And so this allows us to see even further back in time than we normally would using these kind of lousy lenses that nature has made for us. So you'll often see JWST images of galaxy clusters with these arc shapes, and we target them on purpose for that reason. So another reason why I like that image is the reason that we built JWST, the science design case that we had in mind when designing the telescope was to see some of the first galaxies after the Big Bang. And so light takes time to travel. And what this means is that the further away you look, the further back in time you look. And if you want to see some of the first galaxies to form after the Big Bang, you have to look to some of the most distant galaxies that we can see. But the problem is that the universe is expanding. And as light travels through space, the wavelengths of light get stretched. And longer wavelengths mean redder. And so the light gets shifted towards the red. It gets red shifted. And light that was emitted by a galaxy at visible or ultraviolet wavelengths for these very, very distant galaxies gets shifted all the way into the infrared. Another problem with these very distant galaxies is they're also very faint. So the further away something is, the fainter it appears. Because the light gets diluted, it gets spread out. And so telescope mirrors are basically buckets that collect photons. They're light buckets. And the bigger your bucket, the more photons you can collect. So the fainter the thing you can see. And that's why all of these, if you've seen pictures of professional telescopes, they're all like ridiculously hugely big. So JWST has, for a space telescope, a ridiculously hugely big mirror. It's 6.6 meters or 21.7 feet in diameter. And you can see it here compared to Hubble's mirror, it's much larger. One other thing is that it turns out that the longer the wavelength you want to observe, the bigger the mirror you need to get the same resolution. So actually Hubble at visible wavelengths and JWST at infrared wavelengths have about the same resolution, about 0.1 arc seconds. So that's another reason. If you want Hubble-like resolution in the infrared, if you want to see these very small, very faint galaxies, you need a gigantic mirror. And so combining those two things together, the sensitivity to infrared light and this large mirror allows us to see further, to push further out into the early universe to see some of the first galaxies to form after the Big Bang. And so that was the promise, and Webb has been doing that. So this is the Sears field, one of the deep fields that JWST has been looking at. And we're going to play the video here. So this is a visualization of this, taking all of the galaxies in this field, ordering them by wavelength and putting them in a computer simulation so we can use the spaceship of our imagination to travel through the Sears field. And we are going to end up at the furthest galaxy in the field. It's going to be a little red dot, should be coming into view now. And this is called Maisie's galaxy, after the principal investigator's daughter. When your daughter says, "Daddy, can you name a galaxy after me?" I mean, you can't say no. So here it is, this little red blob. We're seeing it as it was about 390 million years after the Big Bang. That's about 13.4 billion years ago. So that light from that galaxy has been traveling to us for 13.4 billion years. Okay. Yeah.
Thank you.
Oh, is that a little better? Oh, okay. Yeah, there we go. So here is the record holder from Hubble. So this is the furthest galaxy that Hubble has ever seen. We're looking at another deep field here. This is the Goods North field. This is a JWST image. Again, look at the stars for the spikes. And that little red, or sorry, yellow dot there is Hubble's furthest galaxy. And it might not look like much, but let me show you the spectrum. So here is a spectra from Hubble of this furthest galaxy. And it doesn't look like much, right? This just kind of looks like noise to me. If you squint, maybe it kind of looks like something. The people who study this assure me that they confirm that this was a galaxy. And maybe for the furthest thing that Hubble has seen, this is okay. Okay, so that's Hubble. There's JWST. So that, even if you aren't used to looking at the spectra of galaxies, that looks like something, right? So you see that nice rise up and then sort of a slope downward, and those little spikes are emission lines from different elements inside of that galaxy. So to me, this looks like the spectrum of a nearby galaxy, and this is the furthest galaxy that Hubble has ever seen. And this is just mind-blowingly cool that it is working this well. It is working better than expected. And I guess as we're going on furthest galaxies, this is the current record holder for furthest confirmed galaxy from JWST. It's actually weird that there's a chance alignment between two galaxies. So this is actually two galaxies on top of each other. The furthest one is the red bit at the bottom that the arrow is pointing towards. And this galaxy, which has the great name of Jade's GS-Z14-0, where it's at a redshift of 14.32, which means that we are seeing it as it was about 300 million years after the Big Bang.
Question?
Yeah.
Am I correct in that some of these latest findings are casting doubt about the age of the universe because these galaxies should not have been able to form in that short amount of time?
Okay, so the question was for everyone online, are these galaxy discoveries casting doubt on the age of the universe because the galaxies should not have been able to form in that time? The answer is no. So these galaxies are slightly different than we were expecting. They seem to be forming stars earlier than we expected, and they seem to be kind of burstier. So they seem to be turning on star formation and then turning them off. And they seem to be forming bigger, brighter stars than what we were expecting. But it's still fits within our general picture of how galaxies formed in the early universe. So this is not like throwing out the Big Bang theory. This is not throwing out our theories of how galaxies formed. This is sort of just adding a little, it's just slightly different than what we were expecting. And so the theorists are all real happy right now because this gives them something to do. And the observers are happy because it's never fun to just go out and see exactly what you were expecting. It's always fun when the universe gives you some surprises. So unexpected, but not like out of the realm of possibility, I guess is how it has been explained to me. And just a final bit on this for this galaxy. So this is the spectrum of this galaxy for completeness, because I'm showing galaxy spectrum. And galaxies have this thing where like blueward of a certain wavelength, basically all of the starlight drops out. This is known as the Lyman break. And that's how we can figure out the redshift and hence the distance to these galaxies. We look for this feature where the light cuts off, and we can use that to figure out how redshifted it has been. So we look at where we observe the light and where the light would be if the galaxy was nearby and resting, and we compare the two, and that's how we figure out the redshift. And we can use JWST's spectroscopic observations to do this. We're not just looking at the colors of galaxies, because sometimes galaxies can appear like redder for other reasons other than redshift. It can have a lot of dust, it can have a lot of red stars or something. This is how we're doing it. We're looking at the spectrum of that, and we're matching the spectral feature. Okay, so that was the most distant things that we can see that JWST was designed to see. Now let's look at the closest things that it can see, the stuff it was not designed to see. So this is actually a really challenging observation. This is a JWST observation of Jupiter. And Jupiter is so stinking bright in the infrared that we have to use the shortest possible exposure we can on JWST and only use part of the detector, not the whole detector, and fiddle around with it. And they managed to do it. They weren't sure if they were going to be able to do solar system planets like Jupiter, but we can, which is great. So here is the JWST image of Jupiter, and we actually discovered a new jet stream in the cloud layers of Jupiter with this observation.
Is that because you're seeing a little deeper into the atmosphere?
I think so, yeah. You're or a different layer into the atmosphere, something like that. I'm not a planetary scientist, so that's like the limit of my knowledge. So here is Jupiter's moon Europa, and Europa is covered in ice, and it has a subsurface ocean. So we knew that, yeah.
On the Jupiter,
yeah.
Picture of Jupiter. Is it real color?
So is this real color? I mean, this is again, it's a 3-filter observation. We take the shortest filter, we color it blue, middle is green, and then the longest wavelength is red. So this is not what you see when you look at Jupiter with your eye, but if you had infrared eyes, maybe this is what you would see, that sort of thing, yeah.
So none of that light is visible.
None of it's visible, this is all infrared, yeah. So again, Europa, icy moon of Jupiter. We know there's a subsurface ocean. We have close-up observations of it, but JWST images allow you to get the big picture. And we also are able to observe in the infrared, where, for example, we can take an IFU image, take a spectrum of every pixel of this image, and we find that there's a concentration of carbon dioxide on that particular area of Europa. And that area of Europa is the youngest area of its surface. There's this thing called chaos terrain where the ice is all broken up. And so that seems to be the youngest ice on the surface of this moon, which tells us that the carbon in this carbon dioxide, yeah, the carbon dioxide probably came from inside of the ocean on this moon. So we knew that there was water. We didn't know if there was carbon, and there seems to be carbon in this subsurface ocean. So those are two things that life on Earth needs. It needs water and it needs carbon. So who knows if there's life on Europa, but we're, one additional piece of evidence that the conditions maybe could be right. Here is an image of Mars. It's not a lot to look at. This again is reflected infrared light from the surface, but you can make out surface features on Mars, comparing it to a map of Mars, we can see the different surface features. And again, it's while we have things orbiting Mars and we have things on the surface, observing it with a telescope like JWST allows you to get a full view of the planet all at once. So here's Saturn from JWST. This is just a one filter image, and we've tinted it orangish, but you can really see the rings of Saturn are reflecting a lot of infrared light. And we also have a couple moons in there. It's really pretty. Speaking of moons, Saturn's moon Enceladus. We have a really neat observation from JWST where we're looking at the plumes coming off. So it's kind of blocky there, but this is water shooting out of the moon. So all of the Saturn system is getting bathed in the water that is coming out of Enceladus, which is pretty cool. So to round out the solar system, we have Neptune here. We have our best view of Neptune's rings since the Voyager flybys. That thing up there that looks like a star is in fact no star. That is the moon Triton. Triton is covered in nitrogen ice, and that is really good at reflecting infrared light. So it's super duper shiny. And so anything that is very small and very bright will have that 8-pointed star pattern, or something like this. Triton just outshines all the other moons. And our last solar system planet, here's Uranus. We have the planet, we have its rings, we have its moons. So Uranus is tipped on its side, and it's coming into the summer on the North Pole. And we're seeing how that white spot at the North Pole, that cloud layer, is changing over time. Comparing it to older observations. Okay, so that's our solar system, but there's many more planets out there than just the ones in our solar system. We know of over 5,000 planets around other stars. We call these exoplanets, and we can observe them with JWST. One method that we use a lot is the transit method. And so we're watching the planet pass in front of its star and then or go behind its star, or both. Again, we're not resolving the planet, we're not resolving the star. There's a single point of light, and we're just monitoring the brightness over time. So it looks something like this. So this is real JWST data. So this is for the exoplanet WASP 39b. It's about 700 light years away. And so we see the brightness of the star is steady, and then it dips down. That's our sign that the exoplanet has gone in front of it, and then it goes back up. Okay, so that's maybe kind of neat, kind of boring. I don't know, it depends on your perspective. The cool thing happens because not only is that planet blocking the light of its star, but also the starlight is shining through the exoplanet's atmosphere. And the atmosphere of that planet absorbs different wavelengths of light, and those wavelengths will depend on the atoms and molecules in the atmosphere of that exoplanet. So it looks something like this. So we take the transit and we break it down by color. And so in this diagram, we see that the red color is getting blocked less. So the transit is a lot shallower. The green color is getting blocked a lot more. So the transit's a lot deeper. But we can do even better than that. We can spread this out by wavelength. So here we have the wavelength of light on the x-axis, the horizontal axis, and then how much light is blocked. So when you see a peak, that is more light being blocked. And those peaks correspond to different molecules in the atmosphere of this planet. So this planet is 700 light years away, and yet we can tell that it has water and carbon dioxide and sulfur dioxide in its atmosphere. So cool. Okay, but wait, there's more. This is a hot off the presses news release. Okay, so we'll go back to this diagram. So when we see the planet transiting, this planet is tidally locked. And what I mean by that is that one side of the planet is always facing the star and one side is always facing away, because this thing, it has an orbit of about 4 Earth days. So it's like ridiculously close to its planet. It's a Jupiter-sized thing, but you'd have a birthday every 4 days if you were on WASP 39b. Okay, so we're tidally locked. We have one side that's always facing the star, one side that's always facing away. But we're also seeing like the transition from night to day, right? We're seeing the terminator. So we have one side, we'll call that the morning side, where we're transitioning from night to day. And we have another side where we're transitioning from day to night. We'll call that the evening side. So you can compare the morning side of the planet to the evening side of the planet. And we actually see that the spectrum, the amount of light that's being blocked, is different. And so this tells us that the temperature on the evening side is hotter. It's about 1,450 degrees Fahrenheit. And on the morning side, it's a little bit cooler, 1,150 degrees Fahrenheit. So a little bit of a temperature difference. Still very hot. Wouldn't want to live there. And so this is really just a proof of concept that we can do this. All of the astronomers I was talking to are really excited that this actually worked. They weren't sure it was going to, but it did. And so now they're going to try to exploit this to learn more about how the energy is circulating, how the atmospheric currents are circulating on these planets 700 light years away. Super cool. Okay, more transit fun. This one is actually a secondary eclipse. So this is the planet TRAPPIST-1b. So the TRAPPIST system is, I think, 7 Earth-sized planets orbiting around a small red giant star. And we want to know, do these planets have atmospheres, or are they like Mercury, like a boring rock just orbiting their planets, right? So one way to do that is to actually watch the planet pass behind its star. So when the planet is beside its star, you're getting the day side of the planet and you're getting the star combined. When it goes behind the star, you lose the planet, and then the planet will come back, and we can see just a little dip there, and that is the signature of the planet going behind its star. Doesn't look like much, but it's enough to figure out the temperature of this planet. And if this planet had an atmosphere, the energy would recirculate around the planet from the day to the night side, and you would have a lower day side temperature on the planet. If it's just a barren hot rock, then it gets real hot on the day side. And the verdict is that this is a barren hot rock, closer to Mercury. So we kind of were expecting this for TRAPPIST-1b, the closest one in, but we're doing all of the other TRAPPIST planets as well to see whether or not they have an atmosphere. Okay, so I could talk about exoplanets all day, but we'll move on to other things. We'll talk about how stars and planets form. So the general picture of how stars form is stars form in these cold, dense, dusty clouds of mostly hydrogen gas. They form clumps, and then those clumps pull in gas, and then they form disks around them. Planets form in those disks, and then you end up something like our solar system or other exoplanet systems. So we'll start in the beginning. We'll observe these very cold molecular clouds, as they're called. And so what we're doing here is we're actually looking at the stars behind the clouds. We're watching the starlight shine through the clouds, and we're subtracting out the starlight to figure out what sorts of things are inside of these cold, dark, icy clouds. And here is a spectrum showing some of the things that we have found. We found ammonia, methane, methanol, all of these carbon-containing compounds. So if you really, really are in space, you need a drink. These molecular clouds are where you want to be. And so it seems that the raw material that stars and planets form out of are just lousy with all of these chemical compounds. And this doesn't imply that there's life. We can actually make all of these carbon compounds without life, which just tells us that they're just absolutely everywhere in the universe. So that's just the cloud itself. We can look at the forming stars inside. So baby stars are actually messy eaters. So the star, so you see the line in the center of the image, that's the disk surrounding a star, a protostar. And the star is pulling in gas from around it. So you'll notice that there aren't a lot of stars in the background, and that's actually the dark, cold cloud as blocking a lot of the light. So it's pulling in gas from around it, and then it's shooting it up above and below, and it's carving out this cavity inside of the cloud. And that's mostly what we're seeing in this image. So it looks something like that. So we have a disk, we have an infalling envelope, and we have stuff shooting out. And if we just highlight the edges of that cavity, it looks something like this. I take away the diagram, it looks something like that, and we can compare it to that. So that's what we're seeing there. Why is it orange and blue? Well, the orange stuff we're seeing through more dust. And by dust, I mean like kind of dust, like things that resemble soot and things that resemble teeny tiny grains of sand. And so more dust is at the top and less dust is at the bottom. So that's why it's orange on top and blue at the bottom. So this is near infrared light. That's sort of the wavelength of light closest to visible light. If we look at longer wavelengths of light, mid-infrared light, it looks like this. And so we're seeing a lot of these soot-like carbon compounds in this image, these polycyclic aromatic hydrocarbons. I like that word. And yeah, so we're seeing this thick layer of dust and these ejections coming out of the star.
Just quick,
yeah.
One of the slides you showed, I think it said 25,000 AUs. This is huge then.
Yeah, this thing is huge. Yeah, where is it? Yeah. Yeah, there we go. Yeah. So yeah, huge. So here, this is a ground-based image of another forming star. It's actually a pair of forming stars known as Herbig-Haro 4647. And it's inside of this Bok globule, this little tiny remnant of a molecular cloud, just a little dark, dusty cloud there. And we have actually two jets shooting out. One you can see rather well because that's outside of the cloud, and there's one actually buried inside of the cloud. And if you look at the bottom left corner, you see a little red thing. That's actually where the jet is leaving. So this is a ground-based image. Invisible light, this is a Hubble image, invisible light, not super impressive. Okay, JWST in infrared light. I know. Oh gosh, this thing is so cool. So in infrared light, we can see through the dust that was obscuring our view. We can see into the cloud and see what's going on. So we see to the bottom left, we see a cavity that's being carved out by a jet coming out of the star. The forming stars, the protostars, are the things making the red spikes in the middle. You can't actually really see them. They're kind of hidden by a dusty disk. And then we see that other jet, the one pointing out of the cloud. And we can see the edge of this dusty cloud, that sort of brown thing, and then the blue thing is light reflecting inside of the cloud. But keen-eyed viewers might see something else. So computer, enhance. Do it again. Enhance. What's that? So some people on Reddit saw this, and it actually made it all the way to the New York Times. So what is this, the cosmic question mark? Our best guess is that it's actually two or more galaxies, background galaxies, that are interacting with each other. This is a Hubble image. It might look something like this. So when two galaxies get too close to each other, they pull on each other with gravity, and it tends to warp them into shapes. And sometimes those shapes kind of look like a question mark. So yeah, not anything to do with star formation, but still kind of cool. Here is another Herbig-Haro object. And this is another forming binary star in the center. We see that dark area, that's the disk surrounding the star, and it's shooting out jets on either side. So yeah, star is there. And so this is kind of ubiquitous. Whenever you have a star forming area, you will see these stars shooting out jets because baby stars are messy eaters. Here's another image. This is a very wide image taken in infrared light with a Spitzer Space Telescope. And we're going to zoom in to just a portion of this with JWST. And so this is another really beautiful image. This was our first anniversary image, and this is showing another site of star formation. So we have a star here. I've labeled this S1, and this star is carving out a cavity. So it's blowing winds, and it's shining very brightly in ultraviolet light, and it is eroding the gas around it. So it's making a little cave for itself to live in. And then if we look carefully, we actually see a whole bunch of jets also from these forming stars. So Rho Ophiuchi is a low mass star forming region. It's the closest star forming region to Earth. And there's actually some other features. If you look at this image, we're going to go sort of to the top of the image, and we can actually see shadows from disks. So we have forming stars, and those stars have disks around them, and that blocks the light. So the light can only shine above and below the disks. So you get these, we call these bat shadows. So you get these bat shadows in the surrounding nebula. So we can see at least 2 of them in this image, which is pretty cool. Okay, more gorgeous star forming images. This is perhaps the most famous Hubble image, the Pillars of Creation. It's a star forming region inside of the Eagle Nebula, and there are stars forming inside of these dark, dusty pillars. You can actually see the pillars getting eroded. So just out of frame at the top are a bunch of young hot stars, and they are blowing winds and they're shining light, and it's causing the nebula around them to evaporate. And you can sort of see at the top that smoky area coming off the top of the pillars. But if we're looking in visible light, our view is being blocked by all of the dust that's inside of the pillars. So if we look in the middle image here in near infrared light, we can see through a lot of that dust, and we can actually now see what's going on inside of the pillars. So we see little stars forming inside. A lot of the pillars have red tips on them, and those again are outflows from these forming stars, a lot like those jets that we were seeing earlier. And then if we switch over to mid-infrared light, we see almost all of the stars drop out. So stars don't shine very brightly in mid-infrared light, most of them at least. We're mostly seeing dust here. We're seeing this cold dust glowing, or maybe warm dust glowing. And this is a lot of those carbon-containing dust, these polycyclic aromatic hydrocarbons. So if you want to understand star formation, you can see through the dust in mostly near infrared light. If you want to study the dust itself, infrared light, mid-infrared light is also where you want to look. So that's why JWST has been so transformational in understanding how stars form. So how do these pillar shapes form? To show this cool animation. So we're inside one of these star forming nebulas. We have a couple stars forming inside. We're going to look at the side of this bubble that these stars are blowing. We have cold neutral gas, and we have light and winds from these stars blowing in, and it's going to erode away this nebula. And so only the densest parts will remain, and the pillars will all point back towards the stars. And then if we zoom out a little bit, we'll see all of these finger-like protrusions all pointing back towards the star. So that's what you're seeing when you're seeing the Pillars of Creation, the sort of last remnants of this star-forming nebula. So these bubble shapes are pretty ubiquitous in star forming areas. So this is a portion of the Carina Nebula. This is off the main nebula. It's this bubble area called NGC 3324. And we're going to look at the edge of one of these bubbles. And so this is another one of Webb's first images called the Cosmic Cliffs in Carina. I really love this image. It's very beautifully composed. It has compelling colors and also really compelling science. So again, we have these hot young stars above the frame. They're shining in on this cold, dusty nebula where stars are forming. And we can actually see it looks like smoke rising out of the mountains. And that's that nebula eroding. And then there are stars forming inside of this brown area at the bottom. If we switch filters and we look at a filter that highlights molecular hydrogen, we can actually see a couple features in here. We actually see these signatures of star formation, these jets and outflows from these young stars forming inside. Okay, again, I could talk about star formation all night, but we're going to move on to another fun topic, how stars die. So stars are born in these nebulas, then they form protostars, and then they take one of a few paths. So for the most massive stars, you will form these hot blue stars. They live fast and die young and explode as supernovas and end up as either a neutron star or a black hole. For the sort of sun-like stars and below, you will not end your life in an explosion probably, unless you have a companion. If you're just a normal single star, you won't explode, and you will end your life as a planetary nebula. And planetary nebulas, I hope you all know, have nothing to do with planets. It's a bad name, but we're stuck with it. It is the last gasp of a dying star. So that's for sort of stars about the mass of our sun. Below that, you don't even get a planetary nebula. You just sort of very boringly end up as a white dwarf. So let's take the sun-like star path first. Here is the Ring Nebula. It's a favorite target of amateur astronomers. And what we think is going on here, this is a visible light image from Hubble, is that we're actually looking down the barrel of this. So it's like donut shaped, and it has a football or rugby shaped thing coming out of the donut, and we're looking right down the center of the donut. And we are seeing these dense knots of dust inside of the donut. So again, that is the visible light image from Hubble. Here is the image with JWST, the near infrared image. The central star, which is responsible for the nebula, is that dot there. There's actually a companion star in a wide orbit that is gravitationally bound to that central star. And we can see these really pretty little features inside these little cometary knot-like things in the donut shape around the central star. And we also see these ray-like things coming off of it. We think that these ray-like things might actually be parts that are shaded from these knots. The knots are shading the nebula from the bright ultraviolet light of the central star, and that's allowing molecules to form in these long linear features, which is kind of cool. Okay, but wait, there's more. So here is the same nebula in mid-infrared light. And if you look on the outside, you kind of see like these concentric circle features. And at first I was like, that looks like an imaging artifact. But actually, no, it's not. It seems to be that these are spaced out. And it seems that there's actually a closer in companion to the central star, orbiting like every 280 years. And as that central star was losing its outer layers, this other star was carving into that gas as it was going out, and it was leaving behind these ring marks. So we have learned something else about the Ring Nebula. There's at least 3 stars responsible for it. So something else with binary stars. This is a more massive star at the end of its lifetime called a Wolf-Rayet star. So this is a very hot, very massive star that is basically blowing off all of its outer layers, and it has a very hot star companion. They're in a binary, they're both blowing winds off, and every now and then in their winds will intersect in their orbit. And for some reason that we don't understand, when those winds collide, it tends to make a lot of dust. It tends to make a lot of that soot-like carbon-containing dust. And it looks like that. So this is real. All of this is real. This is not an imaging artifact. So this is an artifact of that binary evolution of those two colliding winds. And we can count out, there's like 17 shells. And so this is telling us that there's about 130 years worth of dust formation in this image. And it's only occurring like on the right side of the image, not the left. And that's also real. The dust production only turns on in certain points in the orbit, and then it turns off.
It's like a tree ring.
It exactly looks like a tree ring. Yeah, it is basically. So here's a model of the two winds from this. And if you repeat this model, over and over again, so you have one shell and then you make 17 of them, it looks like this. And so this was a model that was developed before the observation. And then they looked at the observation and they're like, well, they exactly match. This is so cool. This was a very early JWST observation, and it's among my favorites. So some other really cool stars at the end of their lifetime, massive stars. This is the Crab Nebula. It is a supernova that we saw on Earth in 1054. We are now seeing the neutron star in the center of the crab and the surrounding nebula. So the neutron star, it's a pulsar at the center there. It's that little white dot. And we can actually look at this supernova remnant in different filters. And we can compare them. So we have three things. We have synchrotron emission, and that's from relativistic electrons spiraling around the magnetic field surrounding this neutron star. Looks like that. We have dust, which are these filaments, which is basically creating a cage around the synchrotron emission. And then we also have sulfur, and that's from the gas. So we're seeing the gas and the dust and the emission from magnetic field lines all combining together to make this supernova remnant, which looks like that. Really cool. So another supernova, supernova 1987A, as the name suggests, it went off in 1987. It is in the Large Magellanic Cloud, and it's that little thing which looks like a little eye at the center there. We can zoom in on it. So that's a Hubble image of the supernova remnant. So there's like a central ring there, and then there's like a figure 8 shaped loop above and below that actually predates the supernova. And the shock from the supernova is running into this structure and lighting it up. So we can actually watch this happen over time. Yeah, there we go. And we can see all these little knots light up as the shock from the supernova passes through this existing structure, which is really cool. Okay, so these are all Hubble observations. Here is the JWST observation. So we can see these features again. We can see this keyhole shape in the center. We can see this ring shape, and then the outer like figure 8 ring. So we think that these rings come from about 20,000 years before the explosion, where we might have had two stars which merged together. And then shortly after that, 20,000 years later, they exploded and made the supernova we saw in 1987. And so 3D, it might look something like that, where you have a central equatorial ring and then two lobes above and below. And something really neat that JWST was able to do is, even though this happened in 1987, it's been observed to death, we haven't been able to find the central neutron star. We think there's a neutron star in the center, but we haven't ever been able to find it. And now we finally have what we think is pretty definitive evidence that it's in there. So this is another IFU measurement. So we are now just looking at emission from a particular line of argon, and we see a bright spot in the center. And so there has to be something very hot in the center, which is ionizing and lighting and causing this gas to glow. And it's so concentrated, it has to be the neutron star in the center, we think. So we finally have what other people assure me is definitive evidence that there's actually a neutron star inside of this thing. Okay, another supernova remnant, another one of my favorites. This is Cassiopeia A. This is mid-infrared light. And what we are seeing here, the orange stuff is mostly glowing dust. The pink stuff is actually shrapnel from the supernova itself. The dust was mostly there before the explosion, and the explosion is expanding outward, shocking this dust, causing it to glow in mid-infrared light. And one interesting feature that we never saw before is you see that sort of C-shaped green thing in the middle. We call this the green monster. And if you look at it really close, you actually see like little circular shaped things. It looks like throwing pebbles into a pond or something. And that puzzled astronomers for a while. They couldn't figure out what this thing is. Why is it at the center of this remnant? What is going on there? Then they took another observation, this time in near infrared light, and it helped solve the mystery. It turns out that the supernova is exploding outward, sort of forming this circular shell, and the green monster just happens to be in a part of the shell that's in front of us. So it's being projected into the center. It's not actually at the center of the remnant. It seems to be part of the wall of this bubble that the supernova is blowing. And those little bubble shapes are where the shock is running into the gas, and the shrapnel from this explosion is running into the gas, and it's making these little circular shapes. Kind of interesting. Another really interesting thing that we see in this this near infrared view is light echoes. And so what do I mean by this? Well, if you have an explosion, that explosion goes outward, it can hit a cloud of dust, heat up the dust cloud, and then those dust clouds will shine back at you. And so you will see the supernova explosion again, but on a delay for things that are behind the supernova explosion. So that's what we're seeing there, the things labeled 3 and 4 on my slides. These look like oil slicks or something. And that is actually dust clouds that are behind the supernova remnant that got hit by the blast of the supernova. They got heated up and then they get reflected back, which is pretty cool. We actually also see this in visible light from the supernova. We're seeing light reflecting off of those dust clouds, and that actually gives us a spectrum of the supernova, even though it happened about 10,000 years ago. Okay, so moving on to galaxies. So we can see star formation happening not only nearby to us in the Milky Way, but also in nearby galaxies. So there's this program called FANGS, which is taking these gorgeous images of nearby face-on spiral galaxies, including NGC 1566, the Spanish dancer. On the left is the Hubble image, and we see blue things. Those blue dots are star clusters. We see pink areas. Those are star-forming regions, and we see brown dust lanes in there in the Hubble image. In the center, in the Hubble image, we see yellow stuff, and that is the older stars at the center of the galaxy. Switching over to infrared light, those yellow stars become blue. So those stars are shining at the bluest wavelength that JWST can see, those old stars at the center. And then we're seeing a whole lot of red stuff, which is mostly just dust. Those are those glowing filaments of dust. It's kind of the skeleton of that galaxy. Here's another galaxy, M74, the Phantom Galaxy. And you'll notice all of those bubbles. And those bubbles are very similar to the bubbles we are seeing in the star forming regions. They are the remnants of supernovas and lots of star formation, basically eroding all of the dust around them, blowing out these circular cavities, which we see as bubbles. Galaxies also, as I alluded to earlier, interact with each other. So this is another of the first images from JWST. This is Stephan's quintet. There are 5 galaxies in this image. 4 of them are interacting. One is a foreground galaxy. The galaxy on the left is actually a dwarf galaxy, which is small but close to us. And the other galaxies are big but further away, and they all look about the same size, just coincidentally. But we actually see those 4 galaxies on the right. They're all interacting with each other. You can see in the middle, there's something that kind of looks like a smiley face. And the top eye of the smiley face is known in the literature as the high-speed intruder. I like that name. So that galaxy is coming from behind and plowing into the other galaxies. And it's creating that pinkish shock front in the middle. That's shocked gas caused by one galaxy ramming into the other galaxies. And if you look at the top spiral galaxy there, you also see the remnants of gravitational interactions, including that beautiful tidal tail going up and to the left. And I will end today on the second anniversary image from JWST, another pair of interacting galaxies known as the Penguin and the Egg, ARP-142. So the Egg is an elliptical galaxy and the Penguin is a spiral galaxy. And the spiral galaxy, the Penguin, is getting warped by the mutual gravitational interaction between these 2 galaxies. And you can see that blue-shaped area. Those are all stars or star clusters getting pulled apart by these 2 galaxies as they interact with each other. So here is the Hubble image on the left of the same galaxies. I think it looks more like a penguin in the Hubble image. You see that beautiful dust lane going from like the beak through the eye of the penguin down through its tail. You don't see that in the JWST image as much because in near infrared light, you can see through dust. In the Egg also looks a little bit bigger. There's also a foreground galaxy that in the upper right corner there, and that galaxy is closer to us and we're seeing it edge on. If you actually go back, so ARP comes from Hulton. Yeah, ARP. Question?
Could you go back to the penguin?
Yeah.
So the penguin's obvious. Is the thing on the left the egg?
Yes.
That's not clear to me before.
Yes, the thing on the left, the
Okay.
circular rugby ball shaped thing is the egg.
I just wanted to make sure.
Penguin guarding his egg. Yeah. So ARP comes from Hulton ARP, who had some very interesting and incorrect ideas about galaxies, but he was also a very great astrophotographer. And so he assembled a catalog of peculiar galaxies in 1966, and that is his image of the Penguin and the Egg. But returning back to the JWST image, we can actually model this in 3D. So here is a visualization of what this looks like in 3D. And as we zoom into the Penguin and the Egg, we can see that the egg has this like pretty smooth 3-dimensional shape. But as we go up to the head of the Penguin, we can see that the disk of this galaxy is being warped and the head is tilting backwards. And that is why it has that rather unusual shape. And with that, that's all I have for you tonight, and I am happy to take questions.
How long have you been at Hopkins?
How long have I been at Hopkins? So I've been at STScI for about 4 years now, which is not quite Hopkins. We're not actually affiliated with the university, although we are on their campus and rent the building from them.
Spring, summer still there?
Yes, he is still there. Yeah, Frank Summers is still there. He actually made the penguin and the egg visualization.
So will we be seeing an awful lot more images coming out in a very short period of time, since it is a 2-year mark?
So we'll be see more images coming out. So we put out our anniversary image, the second anniversary image for the penguin and the egg, but the news cycle continues. And, once every week or two, we put out a press release with new images. So if you would like to follow us on social media at Space Telescope, you will get all of the latest news. There's a question in the back over there.
Oh, yes. I read that the lifespan is 5 or 10 or maybe 20 years. When's the next one? What part of the spectrum is it going to look at?
Okay, so the question was, what's next? So JWST has 20 years-ish worth of propellant on board, so hopefully it'll last about 20 years, maybe more if they really baby it. The next space telescope to launch will be the Nancy Grace Roman Space Telescope. So that sees mostly near infrared light, a little bit into the visible light. What's different is that it has a Hubble-like mirror, but a much wider field of view. So it's something like 100 times the field of view of Hubble, which allows you to take really big, very high resolution pictures of space. So one thing about Hubble is it has this very big high resolution mirror, but only these tiny sensors on it. So it actually, the sensors only take up a very tiny portion of what Hubble can see. So the modern Roman telescope basically has the same mirror, but just puts much larger sensors on it to get a much wider field of view. So that's.
Is it going to be like the Hubble and Earth orbiter, or is it going to be in L2?
It's going to be at L2, yeah. And so that is launching no later than May 2027, probably sometime in 2026, fingers crossed. And then what's next after that? What's the next flagship? And that's what we're planning right now. So the idea that we have for the next great space telescope is called the Habitable Worlds Observatory. So that's going to be like a super Hubble. It's going to see infrared light. It's going to see visible light. It's going to see ultraviolet light. It's going to have a giant mirror of some type, which we haven't determined yet. It's going to be at L2, and its goal is to find Earth 2.0, a Earth-like planet around a sun-like star, and take an image of it. So they're going to observe like the 100 closest sun-like stars to us to see if they can find another Earth. That is probably launching 2040-ish. And so right now they are doing all sorts of engineering about how one would build a telescope like that. And at the same time, the scientists are working very hard at writing a science case for the telescope, and they're influencing each other. Cool, question over there.
What's the signal path for the telescope down to your computer?
What is the signal path for the telescope down to the computer? Okay. I had a slide in here, but I guess I don't have it. So the telescope has a radio signal, which it beams back to Earth. It gets intercepted by the Deep Space Network, which has receivers in California, in Spain, in Australia. And time on the Deep Space Network is always very competitive, and all of the different telescopes have to negotiate with each other. But we get downlinks twice a day-ish. And then that goes from the Deep Space Network to JPL, that gets sent over the internet to Baltimore, to the Space Telescope Science Institute, where all of the data gets processed. And then that gets uploaded to the cloud, to the Amazon Web Services, where then people from all around the world can download it, including our image processors, who then download the data, do all of those things to make all the images beautiful, and then put it up on our website. So, and then I downloaded it from my home today, I guess. That is how I got on the path that the data went.
So what kind of compute power is needed?
what kind of compute power is needed. So the reason why we moved to Amazon Cloud Services instead of trying to host it all on our own servers is that it allows a lot more flexibility. I'm not sure quite how much, but you can like download an entire JWST data set onto a laptop like this and play around with it yourself. The problem is that Roman, with its wide field of view, is going to have ridiculous data rates. And so they are now talking about moving everything to the cloud, including all of the data analysis, because it's going to be too big to download on your computer. And so you're going to have to run everything on a remote server and maybe just download the final science products. And that's going to be a real game changer, both for professional astronomers, and there's actually a lot of amateur astronomers, like image processors, who just wait for something cool to be uploaded to the mass archive, and then they download it and pull it into Photoshop and like make their own JWST images. You aren't going to be able to do that with Roman images. You're going to have to figure out how to use these scientific computational things. It's going to be a lot more difficult. I hope that by the time that this thing launches and we have the science platform ready, that we're going to make some sort of public friendly thing so you all can play around with the data that you have already paid for with your tax dollars. Yeah, question there.
Unless I missed it, I didn't hear you discuss the coronagraph devices on JWST. Which, as I understood it, would allow direct imaging of exoplanets, for example.
Yes. So JWST can take direct images of exoplanets, and I had one in here, but I cut it for time. But yes, you can take direct images of exoplanets, both with the coronagraph, and actually, if you're very clever about how you take an image and then you can subtract the the diffraction spikes off of it, because you know exactly how the telescope behaves, you can actually pull planets out that way too. So astronomers have been doing that as well. You can also use the coronagraph, for example, to block out a star and see the disk around it. So people have been using that to see planet forming disks like around Beta Pic, and they actually see evidence that stuff is colliding inside of this disk and then blowing stuff out. Like within the past 100 years, there was a big collision, and now there's this big dust cloud coming out of it right now. So these disks, which we kind of think of maybe as very smooth and gentle, these things are, violent and changing all of the time. And we can see that because we can use JWST's coronagraph.
So we've got these large molecular gas clouds at star-forming regions. Where was the star-forming region that our sun came from? What happened to it? How did our sun get kind of out there? We're not in the midst of this big cloud, or are we? And I'm just not observing it.
Yeah, so where did the cloud of gas that our sun formed out of? Where is that now? So the sun probably formed in a kind of wimpy cloud, and we can actually dynamically trace all of the stars around us, especially with the Gaia satellite, and look at how everything's moving and see the other stars that are kind of co-moving with our sun that were probably our siblings inside of the cloud. And just after some time, these clouds just tend to disappear because all of the stars forming inside of them shine in ultraviolet light. They have winds, and the clouds just kind of disperse. And then stars at the end of their lifetime output gas back into the interstellar medium, and then eventually that gas cloud cools down, clumps with other gas, and forms new stars. It's a cycle of gas.
Anyone online have a question by any chance?
Not that I see.
Nobody has submitted
You want
a
are
question.
online? You want to unmute yourself?
Nobody has submitted any questions.
Okay.
But if they're online and they want to ask, just speak up, I guess.
Yep.
All right. Kelly, amazing. I mean, beautiful presentation just here, and also you're just so natural with this. So thank you very, very much. Really. All right, guys, we'll switch back here. Unmute. Okay, are you hearing me now? Okay,
Yes.
cool. Excellent. All right, let me see if we can get back to sharing. All righty. All right, so let's do the shallow sky here. It's not a whole lot to go over. If you're interested in the planets and whatnot, Mercury is currently in the evening sky, and it's reaching its greatest elongation, which is the farthest it'll get away from the sun in the evening sky this weekend. However, during the summer and evening, evening elongations are not very great. At sunset, Mercury will be 13 degrees above the horizon, so you'd have to catch it pretty quickly. Probably your best thing would be with binoculars if you wanted to try to get a glimpse of Mercury. Mars is gradually heading towards, I believe it's a December opposition. It's really small. It's in the early morning sky, only 5 to 6 arc seconds. So visually observing, it would be a very tough object. Imaging, you might be able to pull out a little bit of detail, but again, not really a great target. Jupiter is likewise coming from its solar conjunction. It's climbing out of the solar glare. So again, you kind of have to be an early morning person if you want to catch these planets. Saturn is probably your best bet. It's going to be at opposition the first week in September. It's becoming more of a late evening object. It's going to be rising after, actually, I think before midnight over the next couple weeks. So you don't have to necessarily do like I've been doing, getting up at like 4 in the morning to go out and see Saturn. The one thing of note with Saturn is that you're going to have the last Titan transit at 1 in the morning on August the 1st. And you can see from the diagram there, Titan is going to be very low at the South Pole. And what's interesting is that you actually, I don't know that you'd be able to see this visually, but if you want to try to image it, you might have a shot at being able to image Titan as it crosses. Then, because Earth is kind of ascending in its relationship, Titan is going to drop below. So the next several months, Titan will actually miss. It'll be going below the planet. So August 1st, early morning is probably going to be your last chance to see Titan move across the planet for a while. And then, of course, we have the Perseids next month. It's one of the very best meteor showers. I know I was out observing it last year. It was great. It's going to peak this year on the morning, on a work day, unfortunately, Tuesday morning, the 13th. The first quarter moon, the good news is that will set like around midnight. And of course, the best opportunity to see these shooting stars is after midnight. Usually like around 3 or 4 in the morning is a really good time. The radiant is up higher. So if you're interested in catching the Perseids, That's when they will be out this year. One thing to note, you can, if it happens to be cloudy on that Tuesday morning, or, Monday morning works better for you, it's still worthwhile going out because you still get a fair number of meteors. And in fact, there have been times, like in 2021, where there actually was a spike and you saw a higher hourly rate beyond the peak, a day or two beyond, a day or so in front of or beyond the peak. So just because you may get clouded out, I mean, not that that would happen around here, but just in case you get clouded out, you could potentially go either a day before or a day after and still see some shooting stars. Obviously, darkest place possible is usually to your benefit to see the fainter shooting stars. You want to be comfortable, take a lounge chair if you can, maybe even a pillow, but don't fall asleep. And then you might need a light blanket, insect repellent, that sort of stuff might be worthwhile doing. And you really don't need anything. You might want to take binoculars in case you get a really bright one. I caught a really bright fireball the other night that leaves a train. It leaves a little smoke train up there. So, that's kind of cool if you can then take the binoculars and look at it. But when you're looking for the meteors, you don't, just your eyes. Okay, so now, Wayne, if you are ready.
I'm ready. So this month's What's Up in Space is going to be a Hubble status. There's actually two pretty important updates that we need to do for Hubble. One is that in early June, the project decided to go to 1 gyro operations. So to talk about that, I need to do a quick review of the pointing control on Hubble. First of all, the slews are performed by reaction wheels. There are no thrusters on Hubble. So they've got just really large, they're like 100-pound each. They've got 4 reaction wheels. You can see over the diagram over there that they are running with electric motors. And if they change the speed of the reaction wheel, that puts a torque on the telescope and it starts slewing around. So by managing how fast you're speeding up and slowing down the 4 reaction wheels, you can get Hubble to slew to any part of the sky that it can. So again, no thrusters, it's all by the reaction wheels. In order to do these reaction wheels, because there's friction in the system, they will eventually just spin faster and faster and faster. But they do have a maximum speed, and so they have to dump that momentum periodically. And they do that with magnetic torquer bars, which are just big electromagnets up at the top of the telescope tube. And when they energize those and create a current going through these electromagnets, the magnets form a magnetic field, and that interacts with the Earth's magnetic field, and that produces torques on the telescope. And by managing which magnetic torquer bars are activated and how strong, they can then use that torque to then slow down the reaction wheels so that they can have some margin to spin. They also have magnetometers to measure the Earth's magnetic field just as a sensor. It's not actively, I don't think, involved in the attitude control system. But the main thing about the attitude control system is they have 6 what they call rate gyros, and they use 3 of them at a time. And those gyroscopes monitor the pointing and track the slews. As the name says, these gyros do not directly report back what the attitude of the telescope is. There's no fixed coordinate system that they're reporting against. What they do is they tell the ground how fast, or the pointing control system, how fast the telescope is moving and in what direction. The pointing control system then has to integrate that angular velocity to figure out how big of an angle the telescope has moved through since the slew started. And so they can predict and control the slew very carefully using these gyroscopes. These are among the most sensitive, highest accuracy gyroscopes in the world, or out of the world. Next in the line, what's the main? No, not next. Go back, please. Sorry. Go back.
You said next.
Yeah, I did. Next in the slew of the pointing control system are the fixed head star trackers. The gyroscopes don't get you perfectly pointed at the sky where you want to point. So they have some small telescopes that look out the side of the observatory that image the sky, and they use the bright stars and basically do plate solving for those of us who do imaging from the ground. And the plate solve in order to determine the telescope's attitude, and then they send corrections to the pointing control system so that it gets it even closer to within just a few tens of arc seconds. And once it's within a few tens of arc seconds, the fine guidance sensors will then refine the pointing and maintain it for science observations. So that's a 2-minute introduction to the pointing control of Hubble. So next slide. Back in October of 1999, Hubble had 4 of the 6 gyroscopes had failed by October 1999. And science operations then had to stop until the next servicing mission, which happened luckily just a couple of months later. And during that servicing mission, they replaced all the gyroscopes. So that was good. They went back working and just in normal because they knew there was another servicing mission coming up. But in 2004, after servicing mission 4 was canceled after the Columbia disaster, the NASA then developed a couple of contingency modes that would allow science operations to continue in 2 gyro or even 1 gyro. So these were new capabilities that were developed in around 2004. Both of these modes allow science operations to be formed, and as a result, their use will extend the life of the observatory. But both modes have reduced efficiency of science observations because there's just not there's fewer sensors that are used to control the slews and the pointing. So we have longer slew times between targets because, again, fewer sensors, they have to move more slowly or the errors build up too fast. The initial pointing accuracy is less, so the fixed head star trackers have to work harder and maybe have a couple of iterations before they get pointed correctly. And because the initial slew pointing accuracy is lower, there's actually reduced sky coverage for the science observations. Hubble can never point within 50 degrees of the sun, with one exception that I'm not going to talk about. But because of the reduced pointing accuracy, in fact, the slewing accuracy, they have to operationally avoid even a larger part of the sky so that they don't accidentally point within 50 degrees of the sun. There are also certain operational modes that aren't supportable under reduced gyro mode because, among other things, we can't slew as quickly. And there's also, so overall, the observing efficiency in 1 gyro mode, since that's what we're going to be talking about here, is degraded by about 12%. But because of the impacts on the operational modes and the sky coverage type stuff, the overall observatory productivity will decrease by about 20 to 25%. Next. So over on the right, the photograph is astronauts servicing mission 4 replacing a gyro, the gyros. In fact, that silver box just above center is a gyro unit. There's 3 units just like it. And I talked about the fixed head star trackers. Those 3 camera lens-like items are the fixed head star trackers. So they're in the same bay as the gyroscopes. So servicing mission 4 in May of 2009 installed 6 new gyroscopes. So as of now, 3 of those gyroscopes have completely failed. They will not operate at all. And one of the remaining 3 is misbehaving. It gives erroneous measurements, which cause issues and causes the telescope to go into a safe mode, which it has done repeatedly over the last 6 months. And the safe modes are, they're safe for the telescope to be in. They're controlled, but they can't do science when they're in safe mode. So the science program stops. That means observations stop while they investigate and fix the safe mode entry. And the safe mode recovery is also hard on the operations staff. If it happened once in a blue moon, that's not an issue. But when it's happening, every week or 2, that, people don't have lives anymore. So they have decided that they're going to go to one gyro mode and make the telescope operate more reliably. So next slide. So how one gyro operations work is a little bit different. In particular, the magnetometers and sun sensors effectively replace the two missing gyros in a one gyro mode scenario. And then along with the one operating gyro, these sensors will get to within 10 degrees of the desired pointing. The fixed head star trackers then take over and get the pointing to within a few tens of arc second, and then the FGSs tweak it to about 20 milliarc seconds and maintain the pointing through the observation. The other remaining good gyro is not in use, and they're saving it for a time when it's needed to continue science operations. When the one gyro they're using fails, they still have a gyro in the back pocket. And the two gyros are expected to allow operations to continue for at least 5 more years. So the good news is we're going to keep going. The second topic is quite a different kind of topic. Basically, the federal government budget process is a chaotic process in the best of times, and with many political pressures affecting the final budget decisions. This year, fiscal year 25, NASA is facing a reduction, and the astrophysics division is being affected. And the astrophysics division director is trying to strike a balance between new missions and old, and they've set up, among other things, an operations paradigm change review that's going on. As a result of this reduced funding, the astrophysics division is trying to specifically balance investments in missions under development and future missions. So stuff we don't have yet, they're trying to balance those investments against funding for large missions that are in their extended science operations. Now, I've emphasized extended here because it does not, for instance, affect JWST because it's in its primary mission right now. So, but Hubble, however, is in its extended mission since it's been in orbit for what, almost 34 years, over 34 years. So the operations paradigm change review is a part of this process of balancing these investments, and will assess the proposed options for approaches to continue operations of missions in their extended phase with reduced funding. And specifically, they're assessing the potential for limited productivity and decreased operating efficiency of Hubble and Chandra missions under the budget realities. What does that mean? That means they're looking at productivity and operating efficiency impacts on Hubble and Chandra if their budgets are reduced, and they'll examine then the trade between the budgets and where they might be able to take money from future missions or whatever, and the limited productivity and decreased operating efficiency. Okay, so basically this is part of a trade study, and this operations paradigm change review is basically providing an input to that trade study. Now, I've put it on these slides in many places, but it's very important to understand that no decisions have been made yet. The review is ongoing. So this is a little advance notice. Possible decisions from this review and this process could be to maintain the missions as they currently are, fund them like they expected to be funded, and keep operating normally. They could restructure the project in some way or other, or they could just say, it's time to terminate the mission. So next. So the Space Telescope Science Institute has been tasked as part of this process with planning for a budget cut on HST. And this is a little bit of information about what they're thinking about. So the principles they are trying to use is they're going to try to maintain unique UV and optical capabilities, because right now Hubble's the only thing we've got up there for UV and optical, at least at that level. They want to maintain essential mission operations, including standard calibrations and archive support. They want to maintain community grants for science, if possible. And they want to maintain support for broad community access, avoiding bias and inequity. Possible actions that they're talking about, and I want to stress this is not a complete list, but I thought with this group, this might be the ones most relevant. They're planning for understanding the impact of halting Wide Field Camera 3 infrared channel operations. They feel like this can be done because JWST provides infrared observations. They're also looking at what would result from halting of the Advanced Camera for Surveys Wide Field Channel operations, which is a UVIS, UV visible detector, and that's based on that's redundant with the Wide Field Camera 3 UV visible detector. We're also looking at what the impacts of reduction in support for outreach and science communication would be, and possible potential cuts to other instruments or modes within the instrument teams. And again, I want to stress, no decisions have been made yet. This is just a what if situation. So next.
Okay, 2-minute warning, Wayne.
Yeah. Okay. So the OPCR, what's next? The Astrophysics Advisory Committee meets July 23rd and 24th. The meeting's open to the public via telephone using WebEx, and instructions for joining the telecon can be found at that link if you're interested. The OPCR results are planned to be discussed between 11 and 12:15 on Tuesday, the 23rd, with the public comments are specifically scheduled to be discussed from 12 to 12:15. You can also post anonymous public comments, at the link down at the bottom, and you can upvote or on the comments that have already been submitted. So if you're interested and have time, you might consider to call into the meeting to hear firsthand what's being discussed. And you can also, of course, submit your comments. And I just want to end with to remind you that these are your tax dollars being used, so you should feel free to express your opinion, whatever that is, to these public servants. And that's my presentation.
Absolutely, Wayne. Thank you very much for giving us a heads up and how we can hopefully have a participation, at least have our voices heard on that. Okay, let's go to the part of images. And actually, we only got 2 images this month because of all the wonderful weather we've been having. This one here, we have been talking all night about the creation, the pillars of creation. And this is, Jim, your work?
This is my humble image, not to be confused with a Hubble image. Taken not at L2, but at my backyard under a portal 7 sky. Narrowband imaging with sulfur, hydrogen alpha, and oxygen filters. I guess that's about 2 or 3 hours of imaging there with a 4-inch scope with f/4.3 optics.
I mean, that's a beautiful, a beautiful image. You really should be very proud of that. It's gorgeous. All right, my humble contribution from Tuesday morning. We was talking about the Titan transits. Here's one. This was taken in infrared light, and it shows, because basically the seeing was so bad that morning that infrared gives you a slightly better edge against the seeing. I'm really surprised at how dark Titan looks, when you compare it to Jupiter Galilean moon transits. Those are so bright that they almost blend into the cloud background. Here with Saturn and Titan, this first Titan transit I've imaged, nice little dark silhouette there. And that's not the shadow of Titan. That is the disk going across the planet. So again, August 1st, there's another one of these, probably just a little bit lower. I tried, this is with a 10-inch scope. I tried visually to see that. I couldn't because it was so darn close to the edge of the planet. Really just, couldn't see it. Maybe when things shift, the geometry shifts and it begins to transit further north, we might be able to see it. But that was earlier this week. Okay, and I think that's about it. We're not really going to be able to have much of a wrap up. The gentleman that wanted to join HAL, Joel, would you raise your hand? If you would get together, this gentleman said he would like to join HAL. You can at least maybe give him a card or let him know how to do that. Ken, you need to work with the Seestar, right? And folks online, everybody, thank you very much for coming out this evening. Kelly, once again, thank you so much for a great presentation. And we will see everybody again next month. Thank you so much for coming.
Thank you. Bye.
Thank you so much.
Great meeting, very
Yeah.
nice.
Thank
Thanks,
you.
sir. Thank you. Don't forget to stop the recording.
I'm going to try to do that right now. Thank you.